Welcome to my video on 6-8, graphing radical functions. Before we get to that, I'd like to do a quick practice problem on applying the skills of solving radical equations to a word problem. So here we have from page 392, it says for a meteor crater in Arizona, the formula D equals 2 times cube root of V over 0.3, where D is the diameter of the rim in meters and V is the volume in cubic meters. They want to know what is the volume of a crater whose diameter is 1 kilometer across. Okay, so the first thing you should notice on a question like this is the units. The diameter is given to us in terms of meters. The volume is given to us in terms of meters. But the diameter that they give us in the question is in kilometers. So the first thing we should do, judging by the size of this, right, from the picture, is we need to convert. So 1 kilometer is equal to 1,000 meters. So when we make our substitutions later in this question, we should be substituting the 1,000 and not the 1. Okay, so now which variable does this represent? Well, it looks like it's going to represent D, which is our diameter. So I plug in the 1,000 into the equation, and it looks like I have to solve for V, which is kind of trapped under that cube root. So just like we did yesterday with, square root equations, anytime we have a radical of any type, we need to isolate that first. So first I'm going to divide by 2 on both sides because that's not part of the radical, leaving me with 500 is equal to the cube root of V over 0.3. So now yesterday when we did square roots, right, the square root and the square power canceled each other out. So here we have a cube root. So we're going to match the exponent to that index by raising it to the third power. Anytime the index and the exponent match, we could cancel them out. And that just leaves me with the 500 raised to the third power, which is 125 with a lot of zeros. Okay, and now what's left over? Well, we freed up the V over 0.3. And then we finish solving by multiplying by 0.3 on both sides. So we get 3, 7, 5, 1, 2, 3, 4, 5 is equal to my volume. And if we were to actually put a unit on that, that would be under cubic meters. So 37,500,000 cubic meters would be the volume if I had a crater that was 1,000 meters across. Okay, so what is the main focus of this question? Well, I really want you to pay attention to the fact that another way to solve any radical equation is to make sure we match the index with the power that we are using to cancel. Square roots, square powers, cube roots, cubic power. Okay? And that brings us to the lesson for today, which is graphing. So I want you to consider the parent function y equals square root of x. Hopefully you remember from prior to this day that a square root function's graph looks something like that, right? It has a starting point and it kind of swings up. That's what the parent function looks like. So the following are transformations that occur by adding and subtracting values. Remember, if I'm adding or subtracting a value on the outside, we are talking up or down. So radical x plus 2 on the outside of the radical means that we're going to shift the graph up 2 units. Whereas subtracting by 3 outside of the radical is going to tell me down 3 units. Now, anytime we are adding or subtracting inside the radical, right, it's under the radical hat, we're talking about left and right. Now, the one thing to remember with left and right is that it's going to kind of appear to go in the opposite direction of what you think. So if I'm adding plus 2 underneath the radical, I'm going to be moving to the left towards my negative numbers. So this graph would shift square root of x left 2 units. Whereas this graph, x minus 3, right, we're subtracting 3 on the inside, would be going towards my positive numbers, or right 3 units. So now if we actually take a look at the graphs themselves, I have them here. What does that look like? Well, exactly what you think. The parent function of square root of x starts at our origin, right? That is the starting point, and swings out with the arrowhead. Shifting up 2 units shifts that starting point up 2 units. Shifting down 3 units shifts the starting point down 3 units. So when you plug it in, you should see exactly what we just mentioned, right? Plus 2 going towards the negative 2. Minus 3 going towards a positive 3. Okay, so these are all our translations, okay, which are shifts, up, down, left, right. Of course, there's more than just adding and subtracting. We have the ability to multiply by a value. So when I multiply the parent function by a negative, it's like we're multiplying by negative 1. Anytime that happens on the outside of the radical, we're going to say that is a reflection in the x-axis. Okay, so the graph that looks like this is actually going to flip upside down, still with the same starting point, but the bump is going to go in the opposite direction. Okay, now if I multiply by a number on the outside, remember it's going to be a vertical dilation, either a vertical stretch or a vertical compression. Okay, so if I multiply by a 3, that number is big. Okay, on the outside, this is going to tell me that I have a vertical stretch. Okay, so what does that mean? Well, graphically, right, we still have our same parent function. We're stretching it in an up or down direction. So it's like we're going to be pulling this arm up 3. Okay, so you'll see that our graphs kind of swing out much bigger when you're multiplying by a bigger number. Whereas when I multiply by a number less than 1 or a smaller fraction, this is considered a vertical compression. Now, again, it's talking about an up or down switch. So that parent function is almost going to look like it's been stepped on, right? It's going to be pushed down depending on our factor. So you'll see that it'll still curve, it'll still have the same general shape, but it'll be much flatter if I'm multiplying by a number less than 1. Okay, so let's just take a look at those graphs, see how that relates, right? The red is the parent function, so that's right here. If I multiply by 1/2, which is the compression, we see that it is much flatter. When I multiply by the 3, which is the stretch, we see that it's much wider. It even doesn't, totally fit on this particular graph. And when I multiply by a negative value, right, that's our reflection. So you'll see that the exact same curve from our red is going to repeat itself, except it's going to go over the x-axis. Now, if you look at those together, what does it kind of look like? Right? Doesn't it look like a fallen down parabola? Right? So that's going to be similar for many of our radical graphs. It's going to look like a form of the power function, right, on its side. So every rule that we just talked about for our square root functions, right, our translations, our reflections, and our dilations are going to be the same for any other nth root. So we have reflection with an nth root. We have a dilation with an nth root. We have translations with nth roots. And they're going to do the exact same thing. Okay, they're going to have the same purposes. It's just going to be different because the original graph shape is different. Okay, so we need to make sure we know what a cube root graph looks like. Okay, so just as a reminder, to put the cube root into your calculator in the Y1 section, right, we're going to press math, and you're going to choose option number 4. That's going to look like 3 radical parentheses. If you want any other root, you can choose option number 5, which looks like this, and you can do 4th root, 5th root with that. Okay, so when I type this into my calculator, the cube root, we're going to create a table. Now, we're going to plot the main points, right? The ones that are not fractional or decimal, just so that we could keep things neat. But if you need more points, feel free to always graph points on the in-between. So the table that you should see is 1, 1, and 8, 2, which should make sense because cube root and cube, 8 and 2, right, go along with those rules. So negative 8, negative 2, negative 1, negative 1, 0, 0, 1, 1, and 8, 2. Now, when we connect those points together, remember, a cubic power graph kind of looks like that or like that. So our cube root is just going to look like one of those graphs on its side. So when I connect these points, we see that if we turn the page or turn our head, it does look like a cubic graph. Now, it's not exactly the parent function on its side, and we will talk more specifically about this when we talk about inverses, but we should see the same general shape. Okay, so we should be able to graph any one of these functions. And of course, we should also be able to recognize any of the transformations that occur. So I repeated the same slide that we did for our square root functions, and this time applied it to our cube root functions. Okay, but the transformation themselves are the same. This is still up 2. This is still down 3. This is still left 2. And this is still right 2, except it's going to look different because we don't have that starting point and we don't have that arm swinging out. So let's take a look at those graphs, right? Here we have our translations up and down, and that looks like it, right? We have our parent function in red shifted up 2 units to have that middle point right there. Shifted down, middle point right there. Now, the thing to remember is that every single point is being shifted up or down. So if we were to take a look at this and graph it, right, if I were to shift this entire graph up 2 units, 1, 2, I would have to not just shift the middle point, but every point that I have graphed. Okay, and then it does end up looking very similar, to the computer-generated graph that I see. Right? And if I wanted to shift it down 3 units, the same. 1, 2, 3. Has to be every single point. Okay? And that's what it looks like. Now, the left and right are not going to be nearly as pretty. Okay? And that's because when we have these cubic root function graphs, right, the ends are going to be changing really, really fast. So it's going to look like they're almost touching. But if you, again, look at it on its side, you do see that starting point shifting, right, up and down, and all the other points moving left and right accordingly. Okay, so those rules are the same, as well as these, right? This is still a reflection. This is still a vertical stretch. Sorry. This is still a vertical compression. Okay, but what does it look like on a cube root graph? Well, if the original looks something kind of like this, basically what's going to happen here is that everything that was down is going to go up, and everything that was up is going to go down. So the graph is going to look something like this. Okay, now a vertical stretch, if we're thinking about the original, just like with the square root, the bump got bigger. Well, now both of these bumps are going to get bigger, but in opposite directions. So you're going to see it kind of get much bigger up and down with the vertical stretch. And the opposite for the vertical compression. So if we have our original, it's going to be like these are being smushed together. Okay, so it's going to look something like that. Well, that's a terrible one. Let's try that again. has to have the same shape, but look like it's compressed. Okay. So if you take a look at all the graphs, I have done them, right? Here's our stretch, here's our compression, and here's our reflection. So it does follow those patterns. So the last skill you need to be able to do is to identify a parent function from a given equation and figure out what the transformations are without actually graphing it. So if we take a look at this example, the first thing I want you to remember is that this 3 and this 1/2 cannot be combined, right? The 1/2 has a radical attached, the 3 does not. So I'm actually going to suggest that you separate it and, using the commutative property, rewrite it with 3 at the end. Okay? I just made one mistake. So now from here, we should be able to identify all the transformations that are occurring because each number stands for something else. So the parent function is the cube root of x. So that's where this number comes in. This negative tells me we have a reflection in the x-axis, right? Because we're multiplying by a minus. This 1/2 is going to tell me that I have a vertical compression of 1/2. This -2 on the inside, remember, inside is going in the opposite direction, so it should be towards the positives, is telling me I'm moving to the right 2 units. And this 3 on the outside is telling me that I am going up 3 units. So if you can identify each transformation just based off the numbers, you're going to save yourself a lot of trouble as you do these questions. So this is what the graph actually looks like, and it should make sense, right? We're going up 3. We're going to the right 2. It is reflected, right? So the bump is going in the opposite direction from this. And it does look compressed and much thinner, okay? So you can see all of the different transformations at work, working together. So for this section, that's all the notes for this section. There's 2 sets of homework. There's the word problem questions, which you should be able to do. And then, of course, the graphing and the transformations, where I'm going to ask that you graph and describe the transformations for each on our homework. And then when you're done with that, this is the last section on your test coming up. So you can also work on these review problems. You do not have to worry about 23 and 33. Those have to do with rationalizing denominators. And despite what the directions may say, assume all variables are positive if you are working on any radicals that you're reducing.